Hi, welcome to part 2 of creating ionic compounds. Today we're looking at multiple combining capacities as well as polyatomic ions. So these are not exactly exceptions, that's just their exceptionalities. They are exceptional. So they're not breaking any rules, it's just a different type of rule. So some elements, particularly your transition elements, can create multiple ions. So, for example, copper, we can see copper 1 or copper 2. Copper 1 wants to give away 1 electron. Copper 2 wants to give away 2 electrons. And so when we're representing those and we want to build our formula, with copper 1, we would represent it like this. Chloride is always -1. So when we crisscross it, we'll end up getting CuCl. And that those ones are just ignored. So for the copper 2 ion looks like this. It has the 2+ sign on it. Chlorine is always -1. We can crisscross these guys. Which then this 2 comes down and starts to work on the chlorine there. And so we can actually see that it has a different formula. Copper 1 chloride is 1:1 ratio, whereas copper 2 chloride is a 1:2 ratio. So just be really careful about these multiple combining capacities. I'm showing these 1 and 2 as Roman numerals, but without the little caps. Just down the side here, you might want to pause the video if you need and write those down. Those are Roman numerals from 1 to 10. So be familiar with reading, like let's say 4. You can see 4 often with lead and tin. So here we have a formula. Now we want to write out the name. In order to write the name, we have to determine which type of copper this is. Is this going to be copper 1 or copper 2? So what we want to do is actually unzip. And our formula is showing us 1 and 1. So when we unzip, we take this guy up, this guy up. And we want to check. And what we're checking is bromine actually really -1? So we go to our periodic table, we see it in group 7. It's far on the right-hand side. Group 7, they are all charged with -1. So you know what? This is good. If this is good, then this must be correct. The full name of this compound will be copper 1. Bromide. So it's not bromine, we're changing the ending to "ide." So for our second one, now we know something must be up here. So brace yourself. This is a weird one. We're going to unzip. So we're unzipping the formula. We bring the 1 up here. We bring the 2 over here. I lied. This isn't the weird one. We check. Is bromine actually -1? Yes, it is. So we're good. This is copper 2. All right. Now we're on to the weird one. Last one, definitely going to be weird. So in terms of the formula, it's showing us 1 oxygen to 1 copper. When we unzip this and we check, we ask ourselves, does oxygen actually form a -1 ion? And when we go to the periodic table, we'll see it in the chalcogens. It's in group 6. So no, it does not. This is not correct at all. We know that it forms -2. Therefore, if it's a 1-to-1 relationship, if the oxygen's -2, the copper must be +2 in order to be balanced in a 1-to-1 way. So again, we know that because when we crisscrossed, it became -1. But when we look on our periodic table, we know that oxygen never forms a -1 ion. It forms a -2 ion. So we have to backtrack ourselves and say, you know what, how do we get that 1-to-1 relationship? By making sure copper is a +2. Copper 2, and then that'll be oxide. So that guy is a little bit tricky. You always want to check. And now for our polyatomic ions, nitrate doesn't have that ending, that "ide" ending. So that's kind of our red flag, knowing that we're dealing with something that's different. Nitride is like nitrogen, but the ionic form of nitrogen. So this is nitrate. And when we look on our appendix G and H, we'll see NO3 and a -1. Strontium is found in group 2, so SR, and then that's going to be a +2. So in terms of creating its formula, we're going to crisscross. And then when we're rewriting, we'll leave that 1 out. But this 2 needs to work on the entire polyatomic ion. So more than one element is part of this particle, but it works as a whole. So the whole NO3 is, if you will, multiplied by 2. You know, that there's 2 of those nitrate particles for every one of the strontium particles. So we have to make sure that we include these brackets. So we can't have NO32. Somehow it'll end up looking like 32. So let's look at strontium sulfate. So strontium, again, is in group 2. Sorry. And the sulfate ion is SO4, but it's a -2. So when we go to do our crisscross, this is another one where we want to put on the brakes. We should hopefully have a red flag here and go, wait for a second, we got 2 and 2. What does that mean? That means that for every 1 strontium, it's going to give 2 electrons, and 1 sulfate ion is going to receive 2 electrons. So we really only need 1 and 1. So we can reduce this. And ultimately, our formula would look like this. So, no, we don't need the brackets. We don't need the 2 because it's just on a 1-to-1 relationship. Similar to, go back to our previous video with aluminum nitride, where we have 3 electrons being transferred from 1 aluminum to 1 nitrogen atom. So even though 3 are moving, it's still a 1-to-1 relationship. So it's the same thing here. We've got 2 electrons moving, 2 are being lost, 2 are being gained, but it's a 1-to-1 relationship.